Hybrid orbitals result from the mixing of atomic orbitals to form a new set of hybrid orbitals. S, p, and d orbitals can be used. The shape is different from atomic orbitals. The number of hybrid orbitals equals the number of atomic orbitals used in hybridization, and a covalent bond is formed by the overlap of a hybrid atomic orbital or a hybrid orbital. Here's a picture of the s and the p orbitals. If we hybridize these, we form 4 sp3 hybrid orbitals. The 3 indicates the number of p's, and the s, the 1s. Here's the compound methane showing the sp3 hybrid orbitals and the bonding between the hybrid orbitals and the hydrogens. Here's an sp3 hybridized nitrogen atom in ammonia. Notice that the hybrid orbitals, 3 are bonded, 1 has a lone pair. It predicts the correct bond angle. The formation of sp2 hybrid orbitals occurs between 1 of the s's and 2 of the p's. The formation is 3 sp2 hybrid orbitals. They are planar, as in the case of boron trifluoride. The sp hybrid orbital occurs from hybridizing an s and a p orbital. 2 sp orbitals are formed, and they are linear. Beryllium dichloride is an example. To predict the hybridization of the central atom, first draw the Lewis structure of the molecule and count the number of lone pairs and the number of atoms bonded to the central atom. If there are 2 lone pairs and bonded pairs, the hybridization is sp. An example is beryllium dichloride. 3 bonded atoms, hybridization sp2, boron trifluoride. 4 bonded atoms, or lone pairs, sp3 hybridization. Examples are methane, ammonia, and water. 5. Hybridization is sp3d. PCl5 is an example. Bonded atoms are 6. sp3d2. This means 1 s, 3 of the p's, and 2 of the d's are hybridized. SF6 is the example. Here is the relationship between the geometry and the hybrid orbitals. sp is linear, sp2 trigonal planar, sp3 tetrahedral, sp3d trigonal bipyramidal, and sp3d2 octahedral. Here we have a graphic showing the sp2 hybridization of carbon. In the ground state, carbon is 2s2, 2p2. If we promote an electron from the 2s orbital to the 2p and then hybridize it, we have 3 sp2 hybrid orbitals and 1 lone p orbital. The unhybridized 2pz orbital, shown in gray, is perpendicular to the plane of the hybrid orbitals, shown in green. If we look at the bonding in ethylene C2H4, we see the overlap between the hydrogen and the sp2 hybrid orbitals of the carbon. The sp2 and on the other carbon is bonded to 2 hydrogen atoms, and the p orbitals are perpendicular to the carbons. The overlap of the p orbitals forms a pi bond above and below the plane, and then the rest of the bonds are sigma bonds. A sigma bond is the electron density between 2 atoms, and a pi bond is the electron density above and below the plane of the nuclei of the bonding atoms. Here's another view of the bonding, showing the pi overlap. sp hybridization of carbon. If we promote an electron into the p's and then hybridize 1 of the s and 2 of the p's to form sp orbitals and 2 leftover p orbitals, You can see the effect of this in the bonding of acetylene, C2H2. It's a linear molecule. The p orbitals are perpendicular, both above and below the plane along the z-axis and the y-axis. And here is a model showing, a graphic rather, showing the bonding in acetylene. Notice that acetylene is triple bonded. Let's describe the bonding in CH2O. It's formaldehyde. Here's the Lewis structure. Here's a model. There are 3 bonded atoms and no lone pairs on the carbon. The carbon is sp2 hybridized. Here is a graphic showing the pi bonds and the sigma bonds. So the sigma bond is a single bond, the double bond is 1 sigma and 1 pi, and the triple bond is 1 sigma and 2 pi bonds.